Hello everyone. Today we're going to look at the function and its derivative and what they tell us about each other. So here on this graph, you'll see a function, f of x, with various tangent lines drawn at selected values of x. Now what we're going to do to fill out this chart is we're going to look at f prime, which remember that f prime is the slope of the tangent line. And when we look at the particular slope, whether it's positive, negative, or equals to 0, we're going to decide what is our function doing at that point in time. So for when f prime is greater than 0, meaning that the slope of the tangent line is positive, you'll see that the slope of the tangent line is positive here and here. And at both selected values of x, we notice that f of x would be increasing. That means that when the slope of your tangent line is negative, so right here, our function is decreasing. And finally, we have a horizontal tangent line, which is here and here. When our derivative is equal to 0, that's the horizontal tangent, then that's where we have extrema. So f of x has extrema whenever our tangent line is horizontal. Now, when your derivative, right, your slope of your tangent line changes from positive to negative, so that would be when our function changes from increasing to decreasing, that's where we have a maximum. Which by the same logic, if our derivative is changing from negative to positive, that means our function changes from decreasing to increasing, we would have a minimum. Now these are all justifications for what we're going to do now. Whether we're given the graph of the derivative, we can state what the function is doing, or if we're given the graph of the function, we can state information about the derivative. So now, just so you know, sometimes we may need to kind of visualize what the function and the derivative look like in order to answer our questions. So this is kind of like an introduction to what's called curve sketching, which is not exactly a precise visual of your graph, but it's more or less an idea of what our function or what the derivative is doing. So here on this first graph on the left, we have the graph of f of x. And if I wanted to graph the function f prime, right, the derivative, I would have to look at the behavior of my function. Remember that when the function is increasing, which is increasing up to right here, first of all, these are extrema. And when you have extrema, our derivative is equal to 0. So that means we're looking at x-intercepts. Now at first, our graph is increasing, and then it's decreasing, and then increasing again. Now what that means about our derivative is that when the graph is increasing, my derivative is positive. So that means it will lie above the x-axis. In between our two x-intercepts, my function is decreasing, meaning that my derivative is negative, so below the x-axis. And since we have this other x-intercept, we have to make sure that we can connect it. So my derivative would look something like this. So it's negative, and it doesn't matter that it's decreasing then increasing. It just means that we are below the x-axis. So that's that part of the derivative. Then for the last bit, my function is increasing, so that means that my function, or rather my derivative, will have to be positive. So as you can see, what I have in blue, it looks like a parabola, right, which looks like the graph of f prime right next to it. So it's kind of similar concept. So we can expect that if I were to graph the function based on the derivative, it would look something like the graph on the left. But here we go. So when you have your x-intercepts, that means that you have extrema, so either minimum or maximum, and it just depends on what the derivative is doing. Since at x is equal to 0, the derivative changes from positive to negative, that means there must be some maximum at this particular point at x is equal to 0. Now, I don't know exactly where it is, but So it doesn't necessarily matter. I can place it anywhere. Let's just say here. Because remember, this is just a graph of an idea of what my function is doing, not necessarily a precise example. Then over here, where x is equal to 2, my derivative changes from negative to positive, meaning that I have some minimum. Let's just say right over here. Again, does not matter exactly where I place it. Now at first, my derivative is positive until x is equal to 0, meaning that my function will be increasing, which is why I have that maximum. Then between 0 and 2, my derivative is negative, meaning that my function will be decreasing, which is where I get to my minimum. And finally, at the end, after x is equal to 2, my derivative is positive, meaning that my function will be increasing. So this is a general idea of what my function might look like. Now, we're going to practice using our justification. So we're going to answer all of these questions based on the graph of f of x. Now, first we are asked to approximate the value of f prime of 4. Whenever you are asked to approximate, this means to find the slope of the secant line. And the reason we do that is because the secant line runs parallel, if not almost parallel, to the tangent line. And since I don't have an actual equation for the graph that I have, I can't exactly calculate the exact value of the derivative. So we're going to approximate the slope of the secant line. Now, as a reminder, your slope is equal to y2 minus y1 over x2 minus x1. So in order to approximate the value of f prime of 4, remember this is an approximation, so I have to use the symbol for approximation. If I look where x is equal to 4, which is right here, I'm going to pick 2 points on either side. So I'm going to pick f of 3 and f of 5 and f of 3. So when I first write my approximation, I'm going to use my function notation. So I am doing f of 5 minus f of 3 over 5 minus 3. F of 5 is 4. And f of 3 is 0. And then 5 minus 3 is 2. So 4 over 2 is 2. Now, whenever you have to approximate a value, it's good to check what the function is doing at that point in time to make sure that your approximation makes sense. My approximation is positive, meaning that my function would have to be increasing at that point in time, which it is. So we're good to go. Now, at what values of x is f prime of x equal to 0, and then we're going to justify. Remember that we're looking at the graph of the function, and the derivative is equal to 0 where you have extrema. So our derivative will equal to 0 when x is equal to negative 4, 1, and 5. And this is because f of x has extrema at those x values. Now, on what open interval is f prime of x less than 0? Our derivative will be negative when the function is decreasing. So if I look here, my function starts decreasing from x is negative 4 to x is equal to 1, and then decreasing again from when x is equal to 5 until infinity. So the open interval would be from negative 4 to 1, 5 to infinity. And this is because f of x is decreasing. Now, on what open interval is f prime of x greater than 0? And this occurs when my function is increasing. And we can see that it's increasing from negative infinity to negative 4, from 1 to 5. And again, our reasoning is because f of x is increasing. Now, at what values of x does the graph of f prime of x changes from negative to positive? Now, f prime of x changes from negative to positive when you have a minimum. which here, this is at what values of x. So these are not intervals. So we would say that x is equal to 1 because f of x has a minimum. Lastly, at what values of x does the graph of f prime of x changes from positive to negative? And this is when your function has a maximum. So this would happen at x is equal to -4 and 5 because f of x has a maximum. Now we're going to kind of look at the other way around. So here we have the graph of the derivative, and now we're going to answer questions about our function. So on what open interval is f of x increasing? F of x would be increasing when your derivative is positive, so it has to go above the x-axis, which is from -infinity to -2. And this would be because f prime of x is greater than 0. Now, on what open interval is f of x decreasing? This is when it lies below the x-axis, which occurs from -2 to 2, u, 2 to 4. And I had to stop at 2 because at x is equal to 2, the derivative is not negative, the derivative is equal to 0. So that's something else. So if it touches your x-axis, you would have to stop, even if it is negative both times. So we would say that the function is decreasing on this interval because f prime of x is less than 0. At what values of x does f of x have a horizontal tangent? Now, x has a horizontal tangent as long as the derivative is equal to 0. Now, this is the derivative, so it equals to 0 when it touches your x-axis. So f of x has a horizontal tangent at x is equal to -2 and 2. And we would say because f prime of x is equal to 0. Now, at what values of x does f of x have a maximum, and then where does it have a minimum? So first, f of x has a maximum. Now, f of x has a maximum when the derivative changes from positive to negative. So it has to change from going above the x-axis to below the x-axis, which occurs at x is equal to -2. And we would say because f prime of x changes from positive to negative. And then finally, f of x has a minimum when your derivative changes from negative to positive. Now, if you look at your graph, the graph never goes from below the x-axis to above the x-axis. So we would say that f of x does not have a minimum but you would still have to justify. And this is because f prime of x never changes from negative to positive. Now finally, what is the slope of the tangent line to f of x at x is equal to 0? Now what this means is that we're looking for f prime of 0. Now since this is the graph of f prime, I just have to look at the y value when x is equal to 0, which is -2. And last question, what is the slope of the normal line to f of x at x is equal to 4? Now your normal line is perpendicular to the tangent line. So we're going to look, we're going to find what is f prime of 4. When I go to my graph, f prime of 4 is equal to -2. That means that slope of the normal line would be a positive 1/2. Since it is perpendicular, remember that that is the opposite reciprocal. So you change the sign and you flip your number. Now we're going to look at how to find all of this information using an analytical approach, meaning we're going to have the equation and we have to find when the function is increasing, decreasing, has a minimum, has a maximum, etc., just based on the equation. And this is how we would go ahead and do that. So I have some steps here for you. The first step, as always, would be to find the derivative of your function. Then you're going to determine the critical numbers by setting the derivative equal to 0. And critical numbers, you're going to hear me say that a lot, are the x values where there is a horizontal tangent, meaning that that is where you have a possible minimum or maximum. These are also the points where your function could be changing direction, which is why you have a minimum or maximum. Once you figure out your critical numbers, you're going to create a number line with those critical numbers. Then you're going to select test values in between those critical numbers and plug them into the derivative in order to determine the sign. I don't care about the number. We're just looking for when it's positive or negative. If you end up on the interval that it is positive, that's where the function is increasing. And if it is negative, that's where the function is decreasing. Additionally, those critical numbers, if you see on one side you have a plus and the other side would be a minus, then at that critical number you have a maximum, and then the opposite would be if you have a minimum. So let's try this out. We have f of x is equal to x cubed minus 6x plus 1. So first we're going to find the derivative. So f prime of x would equal to 3x squared minus 6. And we're going to make it equal to 0. Once you equal it to 0, we need to solve for x, and these would be our critical numbers. So first I would add the 6. So 3x squared is equal to 6. Then divide the 3. So x squared is equal to 2. And finally, you would square root. So x would equal to plus or minus the square root of 2. Now we're going to create a number line, and we're going to make sure to label what that number line represents. This is my number line for f prime. And I'm going to put both of my critical numbers here. So negative square root of 2 and the positive square root of 2. Now, although I don't know my square root of 2, I know that it's 1 point something. So when I'm picking test values, I just want to make sure that they are in between or rather I choose values that are either less or greater than this 1 point whatever. So let's say I want to test the left side of negative square root of 2. I'm going to plug in negative 2 into the derivative. Remember that the number line represents your derivative. So I have you label it so you can also remember, okay, I'm plugging into my derivative because this is my derivative number line. So if I plug in negative 2 into the derivative, I would get a positive 4 times 3, which is 12, minus 6, which is a positive number. Then if I plug in, let's say 0, 0 is in between negative square root of 2 and positive square root of 2, I would have negative 6 as my derivative, so negative. And if I plug in a positive 2, I would end up with the same as when I plug in negative 2, which means I would have a positive number. This number line tells us everything we need to know. F of x is increasing when on your number line it's positive. So this would be from negative infinity to negative square root of 2. U, positive square root of 2 to infinity. And this would be because f prime of x is greater than 0. Now f of x is decreasing when your derivative is negative. So that means that it's decreasing on the interval negative square root of 2 to positive square root of 2. And this would be because f prime of x is less than 0. Now f of x has a relative maximum at x is equal to negative square root of 2. And this is because f prime of x changes from positive to negative. And finally, f of x has a relative minimum at positive square root of 2 because f prime of x changes from negative to positive. Let's try another example. Now in this one, what's different, not only are we finding increasing or decreasing behavior, but we're looking for the coordinates of the relative extrema. And we're obviously going to provide justifications for all our answers. Now, to find the coordinates of the extrema, you need to plug in your critical numbers back into the original function, not the derivative, because I want the actual coordinates from the function. So here we go. So first I'm going to find my derivative. So f prime of x is equal to 15x to the fourth minus 15x squared. So when here we'll make it equal to 0, what we can do here is we can factor. I can factor out a 15x squared. And when I factor that, I would have x squared minus 1 equals to 0. And I can keep factoring this as well. 15x squared, and then x squared minus 1 is x plus 1, x minus 1, since it is a difference of squares. My critical numbers would be x is equal to 0, negative 1, and positive 1. Now I'm ready to create my number line. I'm going to put all of my critical numbers, so negative 1, 0, and 1. And now I'm going to pick test values in between all of these intervals to plug it in to my derivative. Now when you plug it in, I like to plug it in to the factored version, simply because since I'm only looking for the sign, it's easier to determine the sign once it's factored than by actually having to calculate what the number value is directly from the derivative. So if I plug in negative 2 for the left side of negative 1, this first factor will always be positive because it's squared. Then negative 2 plus 1 is negative, and negative 2 minus 1 is also negative. So positive times negative will give me a positive. Now between negative 1 and 0 would be a negative 1/2. My first factor, positive, second factor, positive, and third factor, negative. So a positive, positive, negative gives me a negative number. Now when I plug in a positive 1/2, my first factor would be positive, my second factor would be positive, but my last factor would be negative. So a positive times a negative would give me a negative. And finally, when I plug in 2, I get a positive times another positive, giving me a positive number. Now I'm ready to start giving all of my information. So first, f of x is increasing on the interval negative infinity to negative 1, u1 to infinity, because f prime of x is greater than 0. Now, f of x is decreasing on the interval negative 1 to 0, u0 to 1, because f prime of x is less than 0. Now remember, because at x is equal to 0, that is a critical number. That means the derivative is equal to 0. It is not less than 0, which is why I had to stop there, even though both sides are negative. Now, to find the extrema, we can see from our number line that x is equal to negative 1. This is a maximum, simply because the derivative changes from positive to negative. And at x is equal to 1, this is a minimum, also because the derivative changes from negative to positive. So now because I want the coordinates, we're going to take those x values and plug it into the function. So first, for f of negative 1, when I plug in negative 1, I get 3 times negative 1 to the 5th minus 5 times negative 1 to the 3rd. This will give me negative 3 plus 5, which is equal to 2. So my maximum is at negative 1, 2. Now I'm going to do the same thing for 1. So when I plug in 1, I get 3 times 1 to the 5th minus 5 times 1 to the 3rd, which is equal to 3 minus 5, so negative 2. So the coordinate of my minimum is 1, negative 2. Now I'm ready to write out my statements. So f of x has a relative maximum at negative 1, 2, because f prime of x changes from positive to negative. And lastly, f of x has a relative minimum at 1, negative 2, because f prime of x changes from negative to positive. Now we're going to look at one more example, and this particular example is a calculator question. So here we have f of theta is equal to theta plus 2 sine theta on the intervals 0 to 2 pi. And we're going to determine the intervals on where it is increasing, decreasing, and again, the coordinates of the relative extrema. So first, I'm going to take out my calculator. Well, first, actually, let's find the derivative. So remember, theta is just another variable, very much like x. So f prime of theta would be 1 plus, and then the derivative of sine is cosine. And remember, our constant, or rather coefficient, just tags along. So it'll be 1 plus 2 cosine theta. And we're going to make it equal to 0. So now in order to find our critical numbers, we're going to go ahead and take out our graphing calculator, and we're going to graph this function. Now, with the derivative, that is. Now, keep in mind that the interval is given to us from 0 to 2 pi. So that's my window. So I'm going to put my x min as 0 and my x max as 2 pi, which is right above this symbol right here. Since it's in blue, I had to click on the second button in order to activate pi. Great. So now another thing that you should always check, especially when you're dealing with trig functions, we're going to go to the mode, and we want to make sure that radian is highlighted. If your degree was highlighted like this, see how it's in black, then we would have to go to radian, press enter, and make sure that it's the radians that we're using, not degrees, or else you're not going to get an accurate graph. So now I'm going to go ahead and put my function. We have 1 plus 2 cosine, and just always use x as your variable. Enter. And now we're going to go ahead and graph it. Now our graph is basically our number line. Our critical numbers are when the derivative is equal to 0, which is your x-intercepts. So we want to make sure we get those x-intercepts down. All right, so we're going to go to second calc and go to 0. It's going to ask you for the left bound, so I'm finding the left critical number first, and then the right bound. It's going to ask you to guess, sure thing, and we get 2.0943. So that is our first critical number. So I'm going to write that down. 0.2, wait, what was it again? Let me check. 2.0, sorry. Okay, so 2.0943, and now we're going to go ahead and find the other critical number. So second calc, go to 0, and now we're going to go to the left side of the other intercept. And the right side, yes, sure, and we get 4.1887. So that's my other critical number, 0.1887. Now we create our number line just as always. We put both of our critical numbers, so 2.0943 and 4.1887, and we don't have to actually plug in any test values. Remember, this is a graph of your derivative. So to the left of 2.0943, it is positive. Then in between our two critical numbers, it's negative, and then to the right of 4.1887, it's positive. So that is for my number line. We still want to create the number line even though we have the graph, because this is typically proof of your analysis. So now that we have our number line, we are ready to start saying our increasing and decreasing behavior. So f of theta is increasing on the interval negative infinity to 2.0943, u 4.1887 to infinity. And then f of theta is decreasing on the interval 2.0943 until 4.1887. Oh, and I forgot to justify. This is because f prime of theta is less than 0. And for when it's increasing, that would be because f prime of theta is greater than 0. All right, now we're ready to find our coordinates. Now remember, our coordinates are when we plug in those critical numbers back into the original function. Now the good thing is, because this is a calculator question, I don't have to actually plug it in and get those values. The calculator is going to do that for me. So first I'm going to find f of 2.0943. So what I'm going to do is go to the calculator. I'm going to go to my y equals. Now here's the thing. If you want to graph more than one function, you most certainly can. As you can see, we have we have different lines here for different functions. And if you wanted to keep this equation, for example, for later use, you would just go to the equal sign and press enter. And you see that it is now not highlighted, meaning that it's saving this equation, but it's not going to graph it until we want to. So here I'm going to put theta, which we're just going to use x, plus 2 sine x. And notice that when I type in my new equation, now this one is the one that's highlighted. So when I graph it, I'm going to only see x plus 2 sine x. And you can see we have a maximum and a minimum here. So really, I didn't need to do all this analysis. I could have just graphed it, but we're doing this just so that we can practice. So I'm going to go to second calc. I want to plug in this number and get the y value, but I don't want to go through all that work. So that is just 1, the value. So I'm going to press 1, and I'm going to put this x value, 2.0943, which is equal to 8264. So 3.8264. This is my, when I look here, this is my maximum. And now I'm going to do the same thing for the minimum. So that is f of 4.1887. So now I'm going to go back to my calculator. And when you're finding a function value, this is the only one you don't have to go back into the calc menu. You can just type in your next value, 4.1887, and we get 2.4567. And this is my minimum. Now I'm ready to write out the coordinates and justify. So f of theta has a maximum at 2.0943, 3.8264, because f prime of theta changes from positive to negative. And now we do the same thing for the minimum. F of theta has a minimum at 4.1887, 2.4567, because f prime of theta changes from negative to positive. And this is how derivatives and their functions are related and how we can get information based on both.